We've looked at the basic ideas of conics, how we define it, how do we find focus, how we find the directrix, tangents, normals, etc., etc. Where the interesting questions come from is when we then try and prove different things. You might remember those questions with parametrics with the parabola, where we had to try and prove certain things. So geometric properties. First one we're going to look at is this idea. The chord of contact from a point on the directrix is a focal chord. Now you notice I haven't mentioned the shape at all. It's true for any conic. So it will be true for a parabola, an ellipse, a hyperbola, and so on. So I'm going to prove it for the ellipse. So how would I do it? Well, they've told me it's from a point on the directrix. So I'm going to define that point to be T. And we're saying, well, look, it's on the directrix. So I know its x value is A on E. Its y value, I don't know. It's that external point, so I'll just call it y naught. We know the chord of contact has the equation x naught, but I now know that x naught is A on E. On A squared plus y naught on B squared is equal to 1. Remember, we're trying to show that it's a focal chord. Well, I've now got the equation of it. If I can show that this line passes through the focus, then it's a focal chord. So if I substitute in x equals AE, y equals 0, and yes, it works. We get 1. So that line does pass through the focus. So therefore, the focus lies on the chord of contact. In other words, the chord of contact is a focal chord. Now we're going to try and make sense of this one. That part of the tangent between the point of contact and the directrix subtends a right angle at the corresponding focus. I'm going to need a picture to explain this one. So let's draw it up. So now let's read that again. That part of the tangent between the point of contact, P, and the directrix, T, subtends. You get 2 points, join up to a third point, that being the focus, and it subtends a right angle. So in other words, PST is a right angle, that's basically saying. So that's what we want to prove. Okay, well, I know the equation of the tangent. I'm doing it in parametric form. So x cos theta on A plus y sin theta on B equals 1 is our tangent. Now we want to find the coordinates of T. So I know that's when x equals A on E because it's on the directrix. So sub that in, and a little bit of rearranging to do there, but we make y the subject, and I've got B outside of E minus cos theta over E sin theta. What a beautiful y coordinate. Okay. So I now have the coordinates of T, I've got the coordinates of P, and of course the coordinates of S is just AE0. If I want to prove that's a right angle, well, slope PS times slope ST, if I can show that's equal to -1. So let's try and do that. Slope PS, just using our standard slope formula. Slope TS, ooh, that one's a bit messier. We've got fractions on fractions. Let's tidy it up. So I'll get the bottom of that, invert, multiply, and we have that. Now, we want to multiply those two things together, but hang on, before I do, because I notice over there what I'm multiplying it with. Remember, I'm going to multiply these two things together, and I want to get -1. So I'd like to see things in the numerator that'll cancel with things in the denominator. And I can see I've got, well, there's cos theta minus E and E minus cos theta. I know that's going to cancel and leave -1. That's good. But other than that, look, the sin theta will cancel with the sin theta. But then I've just got B on A, whereas over here I've got B on A, 1 minus E squared. Well, that's where I'm going to rewrite this A on 1 minus E squared. All I've done is multiply top and bottom there by A. So instead of saying A outside of 1 minus E squared, I'm saying it's A squared 1 minus E squared divided by A. because a squared 1 minus e squared is equal to b squared. Now I've got b squared on a, so now I've got the b squared on a, and I've got the cancelling that I need to get -1. So in other words, what I'm saying is, in order for this to work, I had to use that relationship of b squared is equal to a squared 1 minus e squared. So not immediately obvious, got to rely on our definition of conics to clean up the proof. The reflection property, you might remember the reflection property for the parabola. There is also a reflection property for an ellipse, there's a reflection property for a hyperbola. So we're going to look at the ellipse one. The tangent to an ellipse at a point P is equally inclined to the focal chords through P. So tangent to an ellipse at a point P is equally inclined to the focal chords. Focal chords plural, because we've got 2 foci. So PS dash is one of those focal chords, and PS is the other focal chord. So what we're now saying is angle T dash PS dash is the same as angle TPS. Angle of incidence equals angle of reflection, if you like. I'm going to construct a third parallel line. So there it is, going through P. Now, I'm also drawing in my horizontal there. We know the ratio of PT to PT dash would be the same as PN to PN dash. That's why I drew the third parallel line in. That was basically our ratio of intercepts, parallel lines. Playing around with that, PT over PN would be the same as PT dash over PN dash. Now I'm going to use the definition of our ellipse, or any conic for that matter. Eccentricity times PN is equal to PS. Substitute that in for the PN and the PN dash. We now have this relationship. PT over PS is the same as PT dash over PS dash. But hang on, remember, we just proved that the angle at the focus was 90 degrees. So they're in fact right angled triangles. Have a look at those 2 triangles. Right angled triangles, PT over PS, and then the other triangle, PT dash over PS dash. They're the same ratio in both. We're talking about a right angled triangle where the secant of angle SPT is equal to the secant of angle S dash P T dash. Well, therefore, those angles must be the same. Because we're talking about a right angled triangle. I know both angles, therefore, must be acute. So those angles have to be the same. Alright, let's jump to this little property. What it's basically saying is the sum of the focal chords is always 2A. So PS plus PS dash will always be 2A. And there's a neat little way of proving it. So what we do is we use our definition of the ellipse again. And so I know PS would be equal to the eccentricity times PM. And PS dash would be equal to the eccentricity times PM dash. So now, instead of adding up PS and PS dash, which are 2 lines at an angle, I'm adding up 2 lines, PM dash PM, which are horizontal, and would be the distance between the 2 directrices, which is 2A on E, the E's cancel, and I just get 2A. There's a similar property with the hyperbola, but instead of the sum of the focal lengths, it's the difference. So you'd have PS minus PS dash would be 2A. Which brings us to this little question, which there was one like it, and maybe it was a bit mean setting this question before I'd showed you that idea. It would have been interesting if you worked it out or not. Modulus of z plus 2 plus the modulus of z minus 2 is equal to 8. It's an ellipse. Because what we're saying, let me just draw a picture here to the side. Z is some random point. Its distance to -2 plus its distance to +2 is always equal to 8, is a constant amount. Let me just click back. Well, that's what we just proved. For an ellipse, we've got distance to one point plus distance to another point is a constant amount. It's an ellipse. That's what we got there. Question now is to work out the equation of it. It's centered at the origin, so that makes life a little bit easier. So I know it's a standard ellipse. The focus is at 2 and the other one's at -2. But we also know that the sum of the focal lengths is 2a. So from all that information we should be able to get it. So 2a is equal to 8. So I know a is equal to 4. AE is the focus, that's equal to 2. So I now know the eccentricity is a half. Well, that should be enough to work out b. Remember, b squared is a squared 1 minus e squared. So substitute that in. B squared's 12. I'm not going to worry about finding b because remember the equation of the ellipse is on b squared. So I have my ellipse. X squared on a squared plus y squared on b squared is equal to 1. Okay. It's a nice little question. We are now going to spend not only today but tomorrow as well working on these particular questions, so the different properties, a little bit more challenging than just finding tangents and normals and what have you.